Welcome back to CS Connect series. In the previous video, we discussed about predicate logic. Under predicate logic, we discussed about two kinds of quantifiers, universal quantifier and existential quantifier. We always saw a predicate along with a single quantifier. But in this video, we will see about more than one quantifier that occurs along with the predicate. Say for example, in one of the practice problem, we saw about two variable predicate. So if x and y are going to be the variables that is involved in a predicate, what happens if one quantifier is used with x and another quantifier is going to be used with y? What happens when the order of the quantifiers are getting changed? Every concept with regard to nested quantifiers will be discussed in this video. Let's get into nested quantifiers concept. The order of the quantifiers is important unless all of them are universal quantifiers or all of them are existential quantifiers. When you have two or three variable together in a predicate, say for example, let's have p of x comma y. When it is for all x, for all y, we need not worry about the order of quantifiers because it is going to apply to both the variables. Similarly, when there is existential quantifier that is applied to both the variables, there also you need not worry about the order. When there is a combination of for all and existential together in a particular predicate, there the order of the quantifier is given importance. Based on the order, the meaning of the statement will get changed. Now let's look about the order of quantifiers. Existential quantifier with variable y and universal quantifier with variable x. Q of x comma y denotes the proposition. Let's take x and y to be the domain of real numbers. As for this example, there is a real number y such that for every real number x, q of x comma y. What does this say? They say a particular value of y should be selected and the same y value should be applied to all the values of x. Say for example, if I have y is equal to 1, it should be applied to all values of x here. This is the meaning of this particular order of quantifiers. Now let's take an example. Q of x comma y is equal to x plus y is equal to 0. Do you have any particular value of y for which you can make this particular expression 0? If you have y is equal to minus 2, then for x is equal to 2, you can make it 0. But can you apply minus 2 for all values of x? That is impossible. Since there is no real number y for which we can make this particular statement to 0 for all real number x. No matter what value of y is chosen, there is only one value of x for which we can have this statement. Say for example, if x is going to be 1, then for that 1 you will have minus 1 in the y value. Only then 1 and minus 1 will give you 0. If you take in the context of real number, if we have a value 0.5, then minus 0.5 will make it 0. When we have existential quantification of y variable first, we can state that this particular proposition will have false value because we don't have a specific y value for all values of x. Now let's take universal quantification of x and existential quantification of y. So universal is coming first, existential is coming next. This will denote the proposition for every real number x, there is a real number y such that q of x comma y. So for the same example, let's see this. Given a real number x, say for example, let us take it as 2. There is a real number y such that x plus y is equal to 0. So for this particular 2, we can have minus 2. So from this what you can understand, y will have the value of minus x. If x is going to be 1, y will be minus 1. If x is going to be 5, y will be minus 5. If x is going to be 1.1, y will be minus 1.1. Whatever value you supply in x, the negation of the value will be y. And if you have minus 1.1 in x, then 1.1 in positive sign will be for y because minus into minus will give you plus. So this particular meaning is actually established in this order of quantifiers. So we can say this quantifier with the predicate will make the statement to be true. So for every value of x, you have a different value of y. That is what we get in this particular statement. But here the case is you have only one value of y which has to be applied to all x, which is not possible. Based on the order of quantifiers, the meaning of the statement will get changed and ultimately the truth value will also get changed. Under nested quantifiers, the next topic that we are going to discuss will be negating the nested quantifiers. So when we negate for all, we know it will be changing to existential. When we negate there exist, it will be changing to for all. But what about nested quantifiers? Statements can be negated by successively applying the rules for negating statements involving a single quantifier. So they are asking us to apply this particular negation to every quantifier, taking them to be single at a time. Say for example, if I have for all there exists together, first we have to apply to this quantifier, then we have to apply to this quantifier. Then if a predicate is present here, then it has to be applied here. This is what they say. We have to successively apply the rules for negating statements involving a single quantifier. At a time, concentrate on only one quantifier, apply the rule. Let's go for negation of this particular expression. We have for all x, there exists y, x into y is equal to 1. Now we will see about the negation of quantifier first. When you have negation of existential quantifier, what happens is this existential quantifier will be changed to for all quantifier and this negation will be moving towards the predicate. What about negation applied to for all quantifier here? This will be converting to existential and this negation will be moved to the predicate. This is with respect to a single quantifier. The same thing now we are going to do for multiple quantifiers. So this is moving negation inside all the quantifiers. So let's take the same example that is given here. We are starting with negation in the universal quantifier here. So what is negation of universal quantifier? It is existential quantifier. So this for all will be changing to for some and the negation will be moving to the next part. So now the negation symbol is present here. Negation of existential will give you for all. So this will be for all now and the negation will move to the predicate. Now this negation should be applied inside. This is xy is equal to 1. When I want to negate this, we can have x into y not equal to 1. So we are changing this expression inside the bracket as xy not equal to 1. So this is the negation of the given statement. So we have for all first, then existential next. When you negate, we bring existential first and for all next. First one is with respect to x and second one is respect to y. The same thing we are maintaining. We are not changing the variable. We are working only with the quantifiers. Quantifications of two variables. We will look at the statement. We will learn when it is true and then when it is false, as we saw in single quantifiers. First, let's take for all x, for all y, otherwise for all y, for all x. What did we see in the previous segment? We saw the order of the quantifiers is important unless both belong to the same quantification part. So here we have same quantifiers, here also we have same quantifiers. So we can treat it in the same way. P of x comma y is true for every pair x comma y. This is when it is going to be true. When does it turn to be false? There is a pair x comma y for which this particular predicate will turn false. Now we will see the same statement with existential quantifier. When both are existential quantifiers, there is a pair x comma y for which p of x comma y is true. So there is a pair, here it is true. When do we go for false. P of x comma y is false for every pair x comma y. Now let's get into the nested quantifier part with different quantifiers. First we have for all x, then we have existential y. For every x there is a y for which p of x comma y is true. This is where we saw the statement to be true in case of the example x plus y is equal to 0. So for every x there is a y. When do we say it is false? There is an x such that p of x comma y is false for every y. So here it is for every x and there is a y. The false criteria will be there is an x for every y, but the answer here it will be false. For all is here existential is here, and here we have true. Just the reverse. Here we have existential, here we have for all, and here we have false. Now let's see the other order. If existential is going to occur first, universal is going to occur next. There is an x for which p of x comma y is true for every y. So for a single value of x, it should satisfy all values of y. Now what about this false? Since we have there is an x, we change it as for every x. Since p of x comma y is true here, we change it as false, and it is for every y here. So we are making there is a y. It means for every x there is a y value for which the predicate is returning false. So initially you may have some confusions or complications regarding the understanding. When you work with a lot of examples, you will definitely get used to it. Along with nested quantifiers, we have something called Prenex normal form. A statement is in Prenex normal form called as PNF. If and only if it is of the form, they have given q1 x1. So this is q x. Then we have p of x. This is one quantifier and this is one predicate. When we have q of x1, q of x2, we have p of x1 comma x2. This is two variable. So this is one quantifier and this is one quantifier. We are not sticking to a specific quantifier. It can be any quantifier. But we are marking q for quantifier and p for the predicate. What does this form say? Before the predicate, we have all the quantifiers together. This is Prenex normal form. So q1 x1, q2 x2 up to qk xk, predicate of x1, x2 till xk, where each of qi is either existential quantifier or universal quantifier. Anything can be applied, and p of x1 comma xk is a predicate involving no quantifiers. This part doesn't have any quantifier. All the quantifiers come beforehand. Now let's see an example. We have there is an x for all y. It is in Prenex form. Why? Because all the quantification has applied before getting into the predicate expression. But let's take this particular expression here. For this predicate we have a particular quantifier, and for this predicate we have a particular quantifier. This is not in PNF is what they say, because the quantifiers do not all occur first. That's why we are saying it is not in PNF. Whenever the quantifiers occur before the predicate altogether, that is called as Prenex normal form. Every statement formed from prepositional variables, predicates, truth values true and false using logical connectives and quantifiers is equivalent to a statement in Prenex normal form. It means you can express it in the form of PNF. That's what they say. Now we will get into the practice problem session. Let q of x comma y be x has sent an email message to y, where the domain for both x and y consists of all students in your class. Express each of these quantifications in English. Let's start with existential quantifier in both the places. There is some student in your class who has sent message to some other student in your class. Since we have existential quantification, we are sticking to there is some to some. So it is x has sent to y. So instead of x we have some student and instead of y we have some student. What about the next one? Here we have existential first. So there is a student who has sent an email message to all students because it is given as universal quantifier. There is some student in your class, this is with respect to variable x, who has sent a message to every student in your class is where we apply universal quantifier with variable y. The next one. So whenever you have for all x or for all y, it is every student or all student. When you have existential x and existential y, it is some student or there is a student. Every student has sent a message to some student is what we can infer from here. Every student in your class has sent a message to at least one student in your class. Why do we take it to be at least? We cannot say they sent it to some student. So instead they are making it little bit meaningful. Even if you want to substitute some student, it is not a big mistake. I am just trying to give you in a more formal way. Now let's get into D. There is a student in your class who has been sent a message by every student in your class. Why is the meaning getting changed between B and D? Here X is sending a message to Y. X will be the sender and Y will be the receiver. Here the sender is existential. So we say some student has sent a message. Here Y is the receiver with universal quantifier. So we say the message has been sent to every student in your class. This is existential X and for all Y. Now just take this way. Here we have Y in the first place. It means the receiver is some student. So we can say the message has been sent to some student. But who is the sender? Every student is the sender. This particular variable places are not changed. Even here X is the sender, Y is the receiver. But the quantifier specified here is denoting Y first. So the receiver is some here and the sender is all here. The statement should carry the receiver part first. So we have to say someone has been sent a message. So we say there is a student in your class who has been sent a message by every student. This is the order of Y and X. Now the next one. For all Y, existential X. So the receiver is everyone and the sender is someone. How will we write the statement? Every student in your class has been sent a message from at least one student in your class or from a student in your class. Now let's go for universal quantifier in both the places. Every student in the class has sent a message to every student in the class. So X is the sender, Y is the receiver. So we are going with sent a message. When we have Y in the first place, has been sent is used in order to denote a receiver here and sender here. Next problem. Let W of X comma Y mean that student X has visited website Y, where the domain of X consists of all students in your school and the domain of Y consists of all websites. Express each of these statements by a simple English sentence. So first we have W of Sarah Smith and a particular website att.com. So we have Sarah Smith has visited att.com. It is directly given. So we can have the statement as it is. Now let's get into quantifiers. X has visited www.imdb.org. So we can say at least one student has visited this particular website. So instead of saying one person or someone, we can say student directly because it is given in the context of all students in your school. Y occurs in this place. It means it is denoting website. So Jose Ores has visited some website. We don't know what is that website. So we can say Jose Ores has visited at least one website. Now let's get into D. We have two statements here. W of with a person and W of with another person. So we can say Ashok Puri has visited some website and Cindy Yoon has visited some website. Why have they used conjunction here? It is to say there is a single website which both of them have visited. This is the meaning you have to take. There is a website that both Ashok and Cindy have visited. So that website is nothing but Y. That's why they have specified Y here along with conjunction operation. Or we can tell it in other form. Ashok and Cindy have both visited the same website. Both the statements are giving the same meaning only. Now let's get into E. So let's take Y is equal to David Belcher and W of David Belcher, comma Z. So David Belcher has visited website Z. In this context, W of Y, comma Z will say there is a person Y who has visited website Z. So here Y is actually referring to the person who is visiting the website. Z is nothing but the website, we can say. So combining all these three, that is this conjunction, this particular W of David Belcher and this particular implication, we can say there is a person besides David Belcher who has visited all the websites that David Belcher has visited. Why do we say it is all the websites? Because here we have universal quantifier. So we know Z is going to denote site. Then for all Z will be all websites. If David Belcher is going to visit a particular site, then there is also another person who is visiting the same sites. We can take it like there is a student besides David Belcher who has visited all the websites that David has visited. For every website Z, if David has visited Z, then so has this person. It is not saying that this person has visited only websites that David has visited. They are saying the person may also have visited other websites, but whichever websites David visited, everything is being covered by that person. That's why they mentioned about implication operator. Now let's get on to the last statement. I have just made a correction here. It is actually x not equal to y. Now let's start interpreting this. We will start with W of x comma z by implication W of y comma z. So there is a person X who has visited website Z and there is a person Y who has visited website Z. So this website is going to refer all websites here. What does by implication say? X will visit Z if and only if Y has visited Z. It means both will be visiting the same website. And what does this conjunction say? We say the person X is not equal to the person Y. What can we infer from here? We can infer that X is a different person and Y is a different person. So in this context, you can take it as person or you can take it as student. And since we have there exist in front of X and Y, we can say there is a person X and there is a person Y, but both the persons are not same. So from this by implication, what you can understand, there are two different people who have visited exactly the same websites. For every website Z, one of these people has visited Z if and only if the other one has. It means if X visits Z, then Y will also visit Z. If Y visits Z, then X will also visit Z. This is what they say. That is this by implication operation, if and only if. Next problem. Let S of X be the predicate. X is a student. F of X will say X is a faculty member. A of x comma y is x has asked y a question. It means student has asked faculty a question. Where the domain consists of all people associated with your school. Use quantifiers to express each of these statements. Now let's get into A. Lois has asked Professor Michaels a question. So student has asked faculty a question. This is A of Lois, Professor Michael. Every student has asked Professor Gross a question. So we can take it in this way. A of x Professor Gross, and we know this particular x is going to be universal quantifier because we are taking every student. So this can be for all x. If x is going to be student, we can easily say this is the expression. But here they have given the domain to be all people associated with your school. We have to use the predicate s of x to say that x is a student. S of x implies if x is going to be a student, then that particular student has asked Professor Gross a question. So x Professor Gross is fine, but here this particular implication operation is to specify that this x is a student. Now we have to apply it to all students. So we are using universal quantifier. To say that every student has done this, we need to restrict our universally quantified variable to being a student. This is as opposed to every person because it is given all people associated with school. Make the assertion being quantified a conditional statement stating that only if x is going to be a student, the student is allowed to ask a professor a question. Now let's get into C. Every faculty member has either asked Professor Miller a question or been asked a question by Professor Miller. So when we say somebody has asked Professor Miller a question, so we can have A of x Professor Miller. When we say someone has been asked a question by Professor Miller, whoever asks the question will be coming first. So Miller will be coming first and x will be going next. Who is this x? The x must be faculty member. So which predicate is faculty member? F of x. So we can say f of x implication stating that this faculty member is asking Miller and this faculty member is being asked by Miller. Now they have given or. So when they say or, we have disjunction operation and the faculty member quantification will be every. So for all quantification will be used. Combining everything we have this particular expression. So we have A of x Professor Miller. Then A of Professor Miller x combined by disjunction under implication because the x person must be a faculty member and it applies to all faculty member. Next one. Some student has not asked any faculty member a question. Since we have not asked, it is negation of this particular predicate. Some students means existential x. Any faculty member means it can be anyone or everyone we can take. So it can be for all y. To specify this x is a student, we have to use s of x. To specify this y is a faculty, we have to use f of y. S of x and for all y is for any faculty member is for every faculty member we can take. So faculty member implication, negation of this particular predicate will say has not asked question to any faculty. So this will say has not asked question to any faculty or to all faculty. What about x here? They have said some student. It means it can be one student. So to denote that particular student's quantification, we are using existential. This y is bound only till the faculty part. But this x is bound to the student part as well as the question asking part. Or you can write it in other way. Instead of universal y, you will have negation of existential y, and instead of negation of asking a question, we go with just asking a question. This is another way of expressing it. There is a student such that for every faculty member, that student has not asked that faculty member a question. Next problem. Express each of these system specification using predicates, quantifiers and logical connectives if necessary. Every user has access to exactly one mailbox. We need to rule out the possibility that the user has access to another mailbox different from the one that is guaranteed. We can say access of user to mailbox means user U has access to mailbox M. So how can we write it in terms of specification? User has access to mailbox M, and for all n that is not equal to M, which implies the user has no access. So this is saying the user has no access. This is saying mailbox N is not equal to mailbox M, and we are combining it with conjunction stating user can access mailbox, at the same time except his mailbox he cannot access any other mailbox. So what is the quantification we have to use? It applies to all users and specific mailbox. Here how will you translate this? Every user has access to a mailbox, only one mailbox. So this is universal quantification and this is existential quantification. And regarding this n, we are using universal because except M, every other mailbox will be taken for universal quantification. Next statement. There is a process that continues to run during all error conditions only if the kernel is working correctly. So here we can have h of e as error condition E is in effect. Then we have s of x comma y is the status of x is y. Now let's get into the expression. S of kernel working correctly is this particular statement. This is like P only if Q. This particular part is conclusion and this particular part will be hypothesis. S of kernel comma working correctly. So this is y and this is x. Now they are saying there is a process that continues to run. The status of process is running. So they have given process comma running here. This is talking about this particular statement. Now there is a process. So we are using existential quantifier to process. Since they do not talk about quantifying kernel, we are not introducing any quantification for kernel. Now what is this h of e? Error condition is in effect. It means it is running during all error condition. It means we have to say it is in conjunction. This is happening along with the error condition. So all together this is taken to be the hypothesis and this is taken to be the conclusion. Now since they mentioned it as all errors, we are mentioning this error under universal quantification. So let me remove all the red marks now. So this is combinedly going to give you the hypothesis and this is going to give you the conclusion. So this is for all errors and this is for a single process. Only if is the converse of if. So the kernel's working properly is the conclusion and not the hypothesis. That's what I was also telling you. Now the next statement. All users on the campus network can access all websites whose URL has a edu extension. Website S has extension X is given by E of S comma X. User U can access website S is given by A of U comma S. Now we have to restrict to edu extension. So if the website has edu extension, the student can access all the website. That's what they say. All users can access all the websites. So this all users is universal U and this all websites is universal yes. So here they have given user U and website yes. So we are using universal quantifier in both the places, so we are not worried about the order. In this case, this is also conditional statement because only when the URL has edu extension, all users are supposed to access it. What about the final statement? There are exactly two systems that monitor every remote server. So we have to talk about two systems and we have to say both the systems are not same and we have to say both are monitoring every remote server. There exist two distinct systems such that they monitor every remote server and no other system has the property of monitoring every remote system. M of A B. System A monitors remote server B. The expression is given by for all Z. We'll have for all S M of Z comma S. It means, so this is all remote servers and this is all systems. What is the condition for this particular Z that is given here? The Z can be either system X or Z can be the system Y. Y implication will state that if and only if Z is equal to X or Z is equal to Y, it can monitor all remote servers. That is what is implemented using biconditional. Now what is this and giving? It is telling that X is not equal to Y. Why do they specify this? Because we have to say system X is different and system Y is different. That's why this condition is enforced here. And now we are talking about two random systems. We are not talking about all systems. So it is existential X and existential Y. There is a system X, there is a system Y, but both the systems are not same, but both can monitor all the remote servers is what ultimately we are getting in this statement using this particular expression. It says that X and Y do monitor all servers and it says that no other system does. That's why they have given the condition of Z to be Z is either X or Z is Y. Next question. Determine the truth value of each of these statements if the domain for all variables consists of all integers. So when we say the domain is of integer, we have to consider 0, the positive number and the negative numbers alone. So let's start. We say for all values of n, there is a m. So for every n, there is a m. N square is less than m. Even when you take n to be 10, 10 square, 100 is less than 101. This particular condition will be checked for every integer n. So for every square of n, there will be one integer greater than that. No matter how large n might be, we can always find an integer m bigger than n square. This is certainly true. We can always take m is equal to n square plus 1. The next statement. There is a n, a specific value for all m where n is less than m square. When you want to square 0, you get 0. When you want to square minus 1, you get 1. When you want to square 2, you get 4. So whatever negative numbers or positive numbers or 0 you square up, everything is going to end up with positive only. This statement is asserting that there is an n that is smaller than the square of every integer. So let's take 0, 1, 4, 9, everything. So we can have minus 1 or we can have minus 3. There is at least one integer that is smaller than all the positive integers. We can take it in this way. So this statement is also true. N is not allowed to depend on m since the existential quantifier comes first. So that's why we say n should be selected separately and it should be applied to all m values. This statement is true since n would be less than every square and squares are always greater than or equal to 0. The example in the explanation also stressed the same thing. We said x plus y is equal to 0, where we said when existential comes first, It's for a single y, we apply to all x. The same scenario is given in B. Now the next statement, for all n, there is a m which makes n plus m is equal to 0. This is exactly the problem that we saw in the explanation. M here is allowed to depend on n because existential quantifier is coming in the second place. Since we can take m is equal to minus n, this statement is true. So if we have n is equal to 5, then m is equal to minus 5. Ultimately, n plus m will give you 0. What about D? There is a n. So you have to choose n for all m, which will make n into m is equal to m. Now let's take n is equal to 1. 1 into any number will give you the same number. So 1 n must work for all m. So let's take n is equal to 1 and so the statement is true. If m is going to be 0, 1 into 0 will give you 0. If m is going to be minus 1, 1 into minus 1 will give you minus 1. If m is going to be 10, then 1 into 10 will give you 10. So if it is positive, negative or 0, when you have 1 as n value, this particular expression is true. Always remember, when existential comes first, choose a value, then when all comes next, apply to all. But when all comes first, for all value, when existential comes next, choose a different value. There is a n value and there is a m value. When we square up, we will ultimately get 5. So let's take n is equal to 1, m is equal to 2. So 1 square will be 1, 2 square will be 4, 1 plus 4 will give you 5. So this statement is definitely true. What are the possible solutions? When n is equal to 1, we have m is equal to 2. Then when n is equal to minus 1, we have m is equal to minus 2. Then when n is equal to 2, m is equal to 1. When n is equal to minus 2, m is equal to minus 1. Then the other possibility will be n is equal to minus 1, m is equal to 2, n is equal to 1, m is equal to minus 2. Similarly, n is equal to minus 2, m is equal to 1, n is equal to 2 and m is equal to minus 1. So for both positive integers, for both negative integers, we have 4 solutions. For the combination of positive with negative and negative with positive, we have 4 solutions. So altogether there are 8 solutions to this particular question. We are going to F. There is a n, there is a m. Now they are asking whether it can be squared up for 6. This is actually false because we know 1 plus 4 will give you 5. The next set of value can be 2 square plus 2 square, which will be 4 plus 4, 8. So anything between 5 and 8 is not possible. If m or n were bigger than 2, then left hand side would be bigger than 6. There is no solution. So this particular existential statement is false. And similarly, if we go for 1 plus 3 square, then you will have 10. Then you have 2 square plus 3 square, you have 13. So it goes on more than 6. So this one is false. The next one, there is a n value and there is a m value. N plus m is equal to 4 and n minus m is equal to 1. Actually, we have a solution for this particular problem. The unique solution is n is equal to 2.5, m is equal to 1.5. 2.5 plus 1.5 will give you 4 and 2.5 minus 1.5 will give you 1. But here the domain is for all integers and this is fractional. You are having decimal points. Since there do not exist integers that make the equations true, the statement is false. What about the next one? We have n plus m is equal to 4. Both are existential. And we have n minus m is equal to 2. So in both these problems, we have two conditions. that are combined by conjunction. It means this should be true, this should also be true in order to make this particular statement to be true. So what about this? There is an integer solution to this system, namely n is equal to 3 and m is equal to 1. So 3 plus 1 will give you 4 and 3 minus 1 will give you 2. Therefore, the statement is true. What about the final one? For all n, for all m, there is a p. So what is p is equal to m plus n by 2? We are actually finding the average. This statement says that the average of two integers is always an integer. Let's check. 1 plus 1 is equal to 2 divided by 2 will give you 1. It is an integer. 1 plus 2 will give you 3. 3 divided by 2 will give 1.5. It is not integer always. But this statement is saying when you find the average of two integers, it will always result in integer. If we take m is equal to 1 and n is equal to 2, then p will be calculated as 1 plus 2 divided by 2, which is equal to 3 by 2, which will give you 1.5, which is not an integer. So we know one value of m and n that makes this particular predicate false. So we can conclude the statement is false. Next problem. Express the negations of each of these statements so that all negation symbols immediately precede predicates. It means they are asking us to apply the negations inside all the quantifiers and bring it before the predicates. So bringing it before the predicates is what they mean by preceding predicates. So let's start with A first. So we are starting with negation of the complete expression or the complete statement. First we have to apply negation to this particular universal quantifier. What is negation of for all? It is existential. So we are changing to existential. Now this negation is moving to the next variable and the next quantifier. So now it is negation of existential along with the rest of the statement. So what is negation of existential? It is universal. So we are changing this to universal y and the negation is moving to the next quantifier. What is negation of for all? It is existential again and we are moving it to the predicate part now. So they are asking us to move it till the predicate. So this will be the final answer. Now we will move on to the B problem. We are applying negation to the whole expression. Since we have disjunction here, we are using a bracket in order to specify that. This is in the form of negation of P or Q. So what we will do here is we have to negate P, change this to conjunction and then negate Q. Now we are going to apply it inside. So this negation will be applied to this particular P term. Disjunction is changed to conjunction here. Then this negation is applied to the Q term here. We have to move the negation in both the sides, that is before conjunction and after conjunction. So now for P, this particular negation of universe will give existential. Negation is moving to the next part. Similarly here, this universal is converting to existential after negation and the negation is moving to the other quantifier. Here negation of existential will give for all. So here we have for all and here also we have for all of y. We should not change the variable, only the quantifier should be changed. Now the negation goes and sits in front of the predicate here, in front of the predicate here along with conjunction symbol. This is the answer. What about C? We have implication here. We are applying in front of the quantifiers now. We have to first apply to for all. So this for all will change to existential and this negation will move to the next quantifier. From here it will move to the predicate part. This predicate part is given in brackets. So we are applying it to the brackets completely. And this negation of existential is changing to universal. So this part is perfectly done. Now what is negation of P implies Q? We know P implies Q is negation of P or Q. So now you have to apply negation to negation of P or Q. Negation of negation P, this one will change to conjunction and this is negation of Q. So negation of negation P will give you P, conjunction negation of Q. This is what we get here ultimately. Now this particular term is P and this particular term is Q. So here we are first converting it to this particular format. So this is negation of P. So we are negating it, or Q we are keeping as it is. Now we are applying the negation inside. Negation of negation P of x comma y will change to P of x comma y. Negation of disjunction will change to conjunction. Negation of Q will become negated Q x comma y. So we are removing the brackets here because we are applying the negation inside. So in order to make you understand how this particular transition is happening, I have given it with P implies Q and negation of P implies Q. So we are bringing it to this form finally. That's what you can see here, P and negation of Q. Now let's go to the final sub problem. We have two quantifiers outside and one quantifier inside. So let's start negating. First we have to apply this particular negation inside the quantifier. Now we will start with not of all. What is not of all? It will change to there exist. Now negation has moved to the next quantifier. What is negation of existential? It is universal. Now negation is applied to this particular whole expression. This is in the form of not of P and Q. So we have P and Q here. Negation of P or negation of Q. So we are going to apply negation of P of x comma y. This particular negation with conjunction will give you disjunction, and this particular negation will be applied to existential quantifier here. Before getting to the R predicate, it will be applied to the quantifier present here. So far it is fine. Now this negation has to be changed. So this particular negation will change to for all z, and this negation will move to R predicate. So we have negation of R of x comma y comma z. We are not removing the outer brackets because this is given in terms of the complete expression. These two quantifiers are applicable to the whole expression. So you can apply these brackets here also to say that they are completely one expression. Next problem. Find a counterexample if possible to these universally quantified statements where the domain for all variables consists of all integers. Actually we know what is a counterexample. An element for which P of x is false is called counterexample of universal quantifier. We have already worked with a counterexample practice problem with regard to single quantifier. Now it is with respect to nested quantifier. So we will start working now. For all x, for all y, x square is equal to y square implies x is equal to y. When both the squares are same, they say x is equal to y, and it is applicable to all x and all y. Here they have given the domain to be integers. Actually when x is equal to 1 and y is equal to minus 1, x square is also 1, y square is also 1. So when you have x square is equal to y square, still x cannot be equal to y. So this particular expression cannot turn true. Since the square of a number and its additive inverse are the same, there are many counter examples such as x is equal to 2 and y is equal to minus 2. So here I explained with 1, but here they have explained with 2. So when you have 2 square, it is going to be 4. When you have minus 2 the whole square, it is going to be 4. So here also x square is equal to y square, but x is not equal to y because x is plus 2 and y is minus 2. What about B problem? For all x, there is a y. So for every value of x, there is a different y. Y square is equal to x. When they say y square is equal to x, then what is y? Y should be root of x. This statement is saying that every number has a square root. When you take in the context of negative numbers, This equation has no solution is what they say. Say for example, when x is equal to 9, we know y square is equal to 9. Ultimately, y is equal to 3. This will be the square root. When x is equal to 4, then y is equal to 2. This is the square root. When x is equal to 6, what is root of 6? This root of 6 will not fall under integers domain. So we can say this does not have solution in integers. So what is the counter example? This can be the counter example. What about C? For all x and for all y, x into y is greater than or equal to x. So let's take x is equal to 2 and y is equal to 3. 2 into 3 will be 6. 6 is greater than or equal to 2 is fine. This is fine with positive numbers. What about negative numbers? Since negative numbers are not larger than positive numbers, they have given one example. X is equal to 2 and y is equal to minus 1. X into y will be giving minus 2. Is minus 2 greater than or equal to 2? No. So this can be taken as a counter example. But don't try to have negative numbers in both the places. Minus 2 into minus 1 will give you 2 ultimately and it will make it true. When you are giving a counter example, it should actually make it false. So when you get objective kind of questions asking you to choose a counter example, choose a set of value from the options which will make that particular expression false. Next problem and the final problem. Put these statements in Prenex normal form. Use logical equivalences for prepositions and quantifiers. What is Prenex normal form? You have to put quantifiers first, then have the predicate next. So here you can find quantifiers are sitting in between. Now we have to arrange it in such a way that quantifiers should come out completely and the expression should stay. So let's take A first. They have given an expression where A is a preposition not involving any quantifiers. So only A is free here. Existential quantifiers can be distributed over disjunction. Since it is not involved with any quantifiers, we are leaving out A. So we can use the above statement and turn this particular expression into this format. Along with that, we are inserting disjunction A because A is not going to be involved with any quantifier. We are just putting A inside. This will be the Prenex normal form. What about the next one? We have negation of universal, disjunction universal. Using De Morgan's law and changing the quantifiers. We know negation of P or Q will be negation of P and negation of Q. So now consider this to be P and this to be Q. So negation of P or Q will be negation of P and negation of Q. So we are applying the negation inside. Here it is negation, here it is changing to conjunction and here it is again negation. There is no distribution over conjunction for existential quantifier. So we will rename the variable of the second predicate. Distribution is possible for existential quantification only for disjunction, not for conjunction. You cannot bring this particular existential out because it has no distribution over conjunction is what they say. So instead what we can do is we can rename the variable of second predicate. So this expression will be taken this way. So the first expression will not change, conjunction will stay, and instead of x and q of x we go with y and q of y. Let's apply this and see. Negation of universal will be existential x. This negation will move this side. So it is negation of p of x. And this is again negation of universal. So existential y and the negation is moved to q of y. This will be the final expression. Now bring existential x and existential y outside and then keep negated p of x and negated q of y inside along with conjunction. Why have they done like this? Since we cannot distribute conjunction over existential quantification, we are actually renaming it to another variable. When you want to apply x, it will be applied only to p of x. When you want to apply y, it will be applied only to this q of y part. Though it is negated, it is applicable only for that particular predicate. So P and F can be written in this way without any botheration because we are using another variable there. So this is the answer in P and F form. What about the final problem? We have existential quantification, implication, existential quantification. So first we are changing this into P implies Q will be equal to negation of P or Q. So now this is P and this is Q. So it is negation of P or Q. So this is negation of existential X, or Q will be the Q term completely. So there is no change. What is negation of existential X? It is for all X. This negation is moved to negation of P of X. And this side we don't have any change because there is no negation. The disjunction is staying as it is. Now you have to bring both the quantifiers outside. If you have the same variable, you cannot bring it out. But if you have different variables like the previous sub-problem, we can bring it out. We need to rename the variable of the second predicate. This particular part will stay as it is. The disjunction is also as it is. We are changing existential X as existential Y, Q of Y. This particular part is renamed. Now can you bring it out? Yes, you can bring it out. P and F can be written as for all X there is a Y along with this particular expression. So when it is X, P of X will be used. When it is Y, Q of Y will be applied. So the disjunction operation is not disturbed. This is how we will be able to write P and F form expression. So this is what I was telling you during the explanation part, that every statement can be equivalently expressed in Prenex normal form by making appropriate changes in the logical connectives along with the quantifiers. So this is all about the P and F practice problem. With this we are completing this video. I'll meet you in the next video. Thank you viewers.